Okay. Just to remind everybody the definition of a transpose of a matrix. You have a matrix A, B, C, D. The camera entirely on the right. You have a matrix A, B, C, D, F. The transpose of this matrix just switch columns and rows. Each row becomes a column of the transpose of a matrix. And as you probably remember, if I have R, then the inverse of R, minus 1, is just a matrix such that the product of these two matrices equals to a transformation that, in our context, transformation that doesn't do anything, keeps a point exactly where it is. And we are seeing in the, I don't know how many times, many times, we see the rotation transformation. Plans for today wrap up transformations and start with very exciting and many applications of texture mapping. Texture mapping is fast, would be a very surprising topic, I think, in my book. There's many more applications than originally seen. Okay, we see once again our rotational matrix, and we thought about it a few ways. We got to this matrix originally in 2D by ranking up three geometric qualities. We thought about rotation by alpha plus beta, which has some formulas. Then we got to this rotational way of writing the rotational matrix, which does what? Rotates the whole world by theta degrees counterclockwise. Right. And then we noticed that, hey, I can think about two orthogonal unit vector, u and v. Each vector would be of unit length, and they will be orthogonal to each other. And how would I generate u? I'll take the points x, or the vector x, and rotate it by theta degrees. And similarly, I'll take the vector y, 0, 1, rotate it by theta degrees, and that's how I'll generate v. Well, observe that that's a vector v. And that's, by the way, the coordinates of v when I represent it in the xy Cartesian coordinates, and that's the coordinates of u. But it's a vector, you know. You can generate it in any way you want as long as it has direction and length. It's just one way to represent the vector. And once I did it, I noticed that this matrix, rotation matrix, is represented by y the column of u and y the column of v. And if I do it, it has a few cool ways. The column of u and the column of v. Now I'm trying to convince you that what would be the rotation by theta degrees clockwise. That is rotating by minus theta degrees. Well, I can go back to the original matrix and substitute theta by minus theta, obviously. I can also think about that the product of these two matrices should be equal to the identity matrix. And I can also give you immediately the answer. And the answer would be, think about the vectors u and v that we had originally. And now, instead of writing them as rows, instead of writing them as columns, rows. Now u and v will be the rows. And how can I convince you that this is true? Well, to start with, let's go back one slide. The original matrix took x and moved it to u. What do I expect from the inverse matrix? To take u and rotate it back to x. And is this the impact that I'm getting? Well, let's write u and v and take u as a row, multiply by the vector u. What should be the result? Oh, the result of multiplying the inverse matrix by u. It should take this vector u and move it to 1, 0, which happens to be true because u dot product with u, it's a unit vector. As unit vector, the dot product of the unit vector by itself is a square of the length of the vector, which if it's 1, then 1 square, I can prove it. It's also 1. 1 dot u times u equal 1. And u and v are orthogonal to each other, so u dot product with v will be equal to 0. So this matrix R of minus theta that I happens to write as u and v as rows takes u and transform it into 1, 0, that is x. What happens if I write v over here? Back to our original slide, one slide back. V moves all the way back to y, 0, 1. Does the matrix that I just claimed do all of it? I think so. Correct? Put v multiplied by the same matrix, 0, 1, brings it to y. OK, but how do I know that it's not just that it rotates each and every point to where it should be? Well, it's a linear transformation. If I have a point, and we already had this discussion, if I have a point A, B, call this point P, which is A and B, I can think about it, these coordinates as go in the x direction A units, and then go in the y direction B units. What happened to this point after the rotation? I'll understand this recipe, this algorithm of go A units and then B units as go A units, but now in the u direction. So it's A dot product u plus, and after you reach whatever destination, go B units in the direction of V. R times the point P, AX plus BY, is its linear transformation. It's A times R dot product X, which we just argued. That's just U, R of X, plus B, R of Y, which is V. And it all looks very much, I'm just re-explaining and re-explaining the very same point in 2D, but will be so much easier in 3D. And it will make perfect sense. People, are we good in 2D? All these different way to look at transformations. And we also looked at rotations using complex numbers, which will make sense and will explain itself when we'll go back to quadrillions. But I hope that we'll have a nice discussion about it. Back to translation in 2D. Well, it's not a linear transformation. It's affine transformation, which is why I need homogeneous coordinates. Mind you, homogeneous coordinates, this is not a point in 3D. It's the homogeneous coordinates of a 2D point just written in homogeneous coordinates. How do I understand it? I look at the last number, happens to be 1, and use the formula. Look at the first divided by the last, first divided by the last, second divided by the last, always the last. These are the 2D coordinates of the very same point. And I can write it in a few ways. And in particular, it gives me translations in 2D. And in 3D, we will mostly use it when when I have the camera somewhere in the world, and I want to have my GPU process works on the scene. And the first condition is put the camera in 0, 0, 0. It's not necessary. We'll have a few other transformations, but to start with, put the camera, the eye, at 0, 0, 0. Transform the whole world to 0, 0, 0. How? Translate by minus I. What is a rotation transformation? Now it's in homogeneous coordinates, but in 3D. Homogeneous coordinates in 3D implies that I need 4 numbers. But in 2D, I need 3 numbers. 3D, I need 4 numbers. So the translation of the world by minus I would be 1, 1, 1, identity matrix. Every dot just means a 0 here. What do I have as the last column? Minus I, the x coordinate, minus I, the y coordinate, minus z. Translate the whole world, so the camera moves to 0, 0, 0. Cool? Why do we like so much matrix form? Because for the whole graphical pipeline, we think about this matrix form as something that looks very time-consuming because we multiply one matrix by another, by another, by another, but it's a sequence of operations that we are doing only once for the whole graphical scene. And then we shoot one output matrix to all the vertices of all the triangles or all the processes of the GPUs, and they are all happy with the same matrix. So it saves, actually, tons of time and effort. OK. Transfer rotation around P. How we rotate around P back in 2D? I translate the whole world by minus P. So P moves to the origin. Do the rotation. P moves to the origin. Do the rotation around the origin right now, the matrix that we just saw. And the inverse transformation, which is translate back by plus P. Transformation in 3D, here are the scale matrix, no homogeneous coordinates yet. Multiply the x by s of x, multiply by the y by s of y, z by s of z. Don't influence the other parameters. They just scale up and down, but doesn't change anything else. Shearing transformation, if you remember. Shear, now I just have more parameters. And as we'll see, essentially for our, if you have GPU, it's for the GPU. If you don't have GPU, then for many other algorithms like the Z-buffer, the rastering, clipping works much faster if the camera is at 0, 0, 0, and the look at direction is minus z, and we'll also have an issue of perspective versus orthographic projections. And we would like to move all of it. So the look at is a minus z, and something about canonical volume that we want the transformation, the whole graphic seems to be. For example, we would like to do clipping. If that's our, let me do it again. If here is by I, and that's the volume that I want to render, and as opposed to the ray tracing, you'll always want to specify what the volume that you want to render, and you have a triangle that is outside this volume. Let's not waste time about this triangle that is outside this volume. Only triangles that are inside this volume. If you have a triangle that is partially inside this volume and partially out, I don't want to waste time on the part that is outside the volume. It's not visible. Now, I can check if this is inside the volume or not by comparing it to various half spaces, half planes that define this volume in 2D. But comparing a point even to a half plane is much more expensive than having the volume as -1 and as +1 and -1 in all the coordinates x, y, z, and then think about what happens to this triangle after all this transformation. I just need to check which part of it has z value or y value, which are larger than 1, which have smaller than 1. Much simpler than comparing it to an arbitrary half plane. And other operations that we'll mention are also much easier. Once again, it's much easier to comparing a point and just look at one of its coordinates, x or y and z, and ask, hey, is this larger or smaller than +1, smaller than -1? If it's larger than +1, I don't need to render it. It's not visible at all, not waste time on it. That's where clipping is relevant. But the whole rendering and the depth and the z buffer also would like us to have everything as a canonical way. So to place the whole world into the canonical method, we are not really moving any objects. Specifically, we are just changing the transformation matrix that we feed into the whole graphical pipeline. Same matrix to all the graphical pipeline. If you think all the vertices will see the same matrix. And to express this matrix, I need to understand how to rotate it if UVW, the way that you located the camera, are not on 0, 0, 0. I don't want you to move any objects specifically. You don't need any loop that will say for any object transform this vertex from 0, 0, 0 to from its location to where it should be so that I can place the camera in the right place. It's just think about it as a telescope or some periscope that by which you're doing all the transformation. Think about a periscope like in a submarine that moves your viewpoint from this height to this height. That's what the periscope would be. And essentially, that's what all the transformation matrices do. You're just looking at the world from different point, but from this new point, you pretend that it's 0, 0, 0, and I can apply everything. So you don't really need to remember any of this. Just remember cosines, minus sine, sine, cosine, where the rotation when I was in 2D. Now I'm living in 3D. What happens if I rotate around the z-axis? It means that the z value doesn't change at all. Here's my z-axis as a height. My z value as a height, and I rotate around the z-axis. So I'm just changing the x and y coordinates, but everything that was on a plane with some specific z value shouldn't go anywhere outside its plane. Stay with the same x and y. Z value doesn't change at all. X and y's behave the same way. That's rotation around the positive z-axis. Similarly, cosine minus sine, sinus minus cosine. If I rotate now around the x-axis, so x stays the same, and I applied it for the y and z coordinates, the ones that are changing, and rotate by y, that's the only case that it's different, but that's because of the issue of right hand, left hand. What do you call clockwise rotation? What do you call counterclockwise? Notice here that here it's cosine. Sine minus sine cosine. So it's essentially like rotating by the minus y. What we'll see commonly is that I have the camera somewhere in the world. I have the UVW that you computed already based on homework 3, for example. Look at vector, up vector, you generated UVW. And now you want to perform operation like I see the image right now, and I want to rotate my up vector. So I'll perform a roll operation. I'm standing in the same place, look at the same direction, but rotating the image with respect to this part. Or tilt or pan, the other two types of rotations. And it's going to be a bit more messy than it originally described when we'll want to do animations. Then we'll have to be familiar with this representation called Euler angles more closely, because then between one rotation and animate it in the next rotation, things can go very wrongly if I'm not sensitive about how the angles are represented. But for just changing the view parameters, the camera parameters, I don't need to be so careful about how I represent it. So what do we do about an arbitrary rotation? To rotate around the x about any axis where I'm looking at, I want to rotate the image where I'm looking at. What I'm going to do is I want to use orthogonal matrices, and I want to first rotate the joke, mathematician, teacup, etc., etc. I'll rotate it first, not by the roll operations that I want to do. I'll rotate it so the UVW will be aligned with the XYZ coordinate. Again, my work plan is, even though all I want to do is the camera is right here and I'm doing my roll operation, I'll first rotate it so I'll assume that the UVW are aligned with the XYZ. How do I do it? Very simple. UVW you already calculated in homework 3. Look at these three vectors, UVW. They are orthogonal to each other. U dot product U equals 1, U dot product V equals 0. And now just write the rows UVW. That's a rotation matrix that you need, not for the roll. For aligning the camera, let's attempt to write it. But I have two tools. I have rotate around the X, rotate around the Y, rotate about the Z. That's one tool. And I have another tool that says, if you want to transform from one basis to another, represent from one coordinate to another, just write down the coordinate. And it's easy to confuse between them, so don't. This will be the boring tool, and I don't want to make it any more complicated than I have to. You want to do rotation around arbitrary matrix? Just think about the matrix R of U, R of V, R of W. Again, don't confuse. My goal essentially is to do, let's stick to the purpose. I want to perform Perform roll by 30 degrees given some arbitrary UVW. How can I do it? UVW are arbitrary. If I'm going back to my three matrices, then in general, now it's not the X, U and the W are nor the X, nor the Y, nor the Z. I cannot use these tools directly. So what should I do instead? I'll write a matrix that consists of U as a row, V as a row, W as a row. That's all you need. What is the impact of this matrix? Where does this matrix take the vector U? Help. If I feed this matrix to the vector U, multiply this matrix by U, 1, 0, 0. U dot product U is 1. U orthogonal to V, U orthogonal to W. So this matrix takes U into X. It will take V into Y, right? Because V dot product this creature gives me 0, 1, 0. And it will take W into 0, 0, 1, into the Z direction. What would be the inverse? R minus 1, take this matrix and switch rows with columns. Right, U, V, W, but now as columns. That's the inverse of this matrix. Now, help. How do I obtain this task of, given arbitrary U, V, W, which matrix, and I don't need the answer as exact coordinates, give me a product of these matrices so that I'll perform rotation. I want to be able to say M times MP would take P and rotate it by 30 degrees with respect to UVW, like rotate roll of P. M of P is the roll operation, is rotate around, we'd say the rotate around W, roll, I'm watching at this direction, changing my up vector. Is rotating around roll by 30 degrees. Okay, what is M? Give me express M as a product of three matrices. And it will be the same expression no matter what is UVW. I will assume here that the I is already at 0, 0, 0, otherwise I need to start and end by translation. I will assume that the I is already at 0, 0, 0. So it's only rotations involved. Help? M equals two coordinate systems. UVW, arbitrary rotation, XYZ, arbitrary rotation. I'll hold them differently, but assume the 0, 0, 0 is the same, common to both of them. So it's just to take this one and make it snug, so it's aligned with the first one. Yeah?
So the first step would be to multiply by, I think, R UVW?
Exactly. That would be R U V W that I needed to take U and make it aligned with the U with the X coordinate. So that would be U V W. That would be the first matrix. I still need something here at the middle. I'll end by do the inverse rotation, which is somebody else? R inverse, which in general, computing inverse is a pain. But because these are rotational matrices or orthogonal bases, what is this one? U as a column, V as a column, W as a column. What happens here? What happens here in the square? After applying by the first matrix, rotate by Z by 90 degrees, by 30 degrees. Right. So that would be the cosinus 30, etc., etc. 0 sinus 30, etc. And 0, 0, 1. This is exactly this guy. So what did I do altogether? Started from here, rotated it so it's snagged, and then do the rotation around the Z, and do the inverse. And if the I is not in the same place, then I need to start and end by translate the I to 0, 0, 0, and then move the I back to the original location. OK. We covered this part. Okay. General location, just translate once again, move the I to 0, 0, 0, and then translate, and then rotate, but the rotation is just use this magic of write the coordinate system altogether. We can skip this part. Actually, OK. So we have a few more steps in the transformation. We want to move the I. We want to rotate it. So it's X, Y, Z. We want to control everything. So it's in the canonical volume. I'll actually talk about it a bit more. But this part needs more explanation. That we like to watch the world using perspective coordinates. That's how the image should be. Like things that are further away should look smaller. The GPU would like to only project by straight line, projective transformation. So here is my image plane, and this pixel sees only thing that happens on this horizontal line. All these points have all the same X and Y volume. Much simpler for the calculation. But orthographic projection on the plane, on the image plane, and the image plane would be orthogonal to the z-axis. So we like perspective. GPUs would want everything as orthographic. So let's have our first attempt to project everything onto the image plane. And here it actually will be perspective, but I want to know for every point P1, X, Y, Z, if I project it into the image plane, and the image plane is at Z equal D, to which pixel this point will hit. That is, away from the I now at 0, 0, 0, away from the I toward P1, which pixel will it hit? And that's going to be very, very simple to represent. Unfortunately, it's not exactly what I need to represent. But that would be very simple to represent, and it's once again, we are using the power of homogeneous coordinates. It's the second usage of a homogeneous coordinate. with homogeneous coordinates first for translation. Here is another reason why we want homogeneous coordinates. So input some point on the world, x, y, z. Output a point on the image plane. I'll tell you the image plane is all in the plane z equal d. All these points have the same z value, which is d. What is x1? y1 goes your direction. y1 goes this way, so computed in the same way. So I'm just playing with x and x prime. What do I know about this triangle versus this triangle? 8th grade, I assume. This angle 90 degrees, this angle 90 degrees. This angle equals this angle, congruent similar triangles. So this divided by this, that is x1 divided by z1, should be x1 prime divided by this distance d. x1 divided by z1 should be x1 prime, the pixel that it falls into, divided by d. And I know what is d. I decided where to place the image plane. So x1 prime is just d times x1 divided by z1. All great, but it's not a linear transformation. Not in the Cartesian world. I don't know to express it as multiplication by a matrix if I insist on my similar and fuzzy, warm and fuzzy Cartesian coordinate. So I'll go to homogeneous coordinates. Everybody understand how did I get to compute x1 prime and y1 prime? What are the location where this point is projected into? We are good into this box. Here is the matrix that I'll use. Identity matrix all the way over here, 1, 1, 0. I'm living in 3D, so 4 coordinates. And the only difference is that here I'll write 1 over d. So usually when I'll give you a point x1, y1, z1, and I'll tell you express it in homogeneous coordinates, what will you write as a w? You'll just write 1. Why not? Multiply this guy by this guy. What are we getting? In the first line, we are getting x1, y1, z1. And what happens in the last one? That's where the action is. Last one would be z1 divided by d. How do we understand this vector? We want to bring it back to familiar Cartesian world. We want this number to be 1, so we'll divide each one of these 4 numbers by the last one, making it x1 divided by whatever you have here, z1 divided by d. Same for y1, same for z1, and the last one is just 1. So it does exactly what I want. So the output would be z1 divided by z1 over d is what? Just a tedious way. This is a very tedious way to write d. So all the points will have z equals d, and I'll just generate the right points. And something like this is useful when you're projecting things and play with texture, for example. We do need such matrices, but if we want to, and it doesn't necessarily go through the orthographic projection, but what's the problem here? The hidden surface removal. Right? I have 2 triangles. My GPU per every pixel, my Z-buffer algorithm, no matter how you implement it, needs to decide for every pixel, for these 2 triangles, which one comes before which. If this part belongs to one triangle, this part, but also for another triangle, I have 2 points that are projected to the same pixel. The GPU cannot know which one is further away. You can calculate the distance, shoot array, etc., but it's all very slow. Okay, this type of transformation will find a use, but issue, we don't know which one is further away from which one. So what we actually need to use is a perspective warping. And that's much harder to understand, arguably. So I did what I usually do when I don't understand things. GeoGebra is a very easy way to implement everything. Very quick way. I needed to, and it also shows us what is this canonical volume that I'm talking about. You represent the near, you represent the far. Near here, I'll represent just as a distance. Usually you'll write everything like what is a corner, near, upper left, far, lower right. And then you're pretty much done. Presumably that this is a fastrum. That is, it's a chopped pyramid, and this plane is parallel to this plane. Like in 3D, this plane parallel to this one. And all that you're going to view are points that lives inside this fourstum. Only point here needs to be visualized. I want to project them where the image plane starts at -1 and ends at 1. The image plane in 3D will be -1, -1, -1, and 1, 1, -1. Z will be -1. But mostly, I need everything to be to use projective transformation. So I'll have a set of points here that are all projected into a pixel, and orthographic transformation. Did I say projective? So the ZPU would like to have, here is the image plane, and what I'll assign to this pixel is just the nearest object, but this should be horizontal in this image. That is directed in the W, in the -z direction. That's for this pixel, that's for this pixel. So I need some transformation that is take this whole volume, every point that lives inside this volume, and project it into other points which will be inside the volume, but from which, if I just ignore the z value, it will just be projected into the image plane. And for this, we are using this surprising transformation. Near plus far. There's a distance to the near plane and the far plane. You as a user determining what is the near and far, or otherwise you are computing the near and far based on the angle field of view. Far times near minus 0, 0, 1, 0. Why does it work? What transformation does it have? It was very unintuitive, I think. So here are a set of input points. The green points over here are all input points. And giving the eye over here, they all need to be projected into the same pixel. I'm still in perspective world. They all need to be projected into the same perspective. But I want to use orthographic projection, so I'll first transform all these points into other set of points, still in 3D, using the matrix that you see over here. And these points and these points should correspond to each other. In what way? The Z buffer asks what? I rendered I rendered this pixel as green because I saw a green triangle over there. And then if I'll inject a red triangle, I will not change the color of this pixel because the distance to the red is larger than the distance to the green. So I will not change the color of this pixel because of z-value arguments. But I want to only look at the z-values. I don't want to look at the x and y. So these are only compare pixels over here. And that's what this matrix is doing. So what will be the properties? Look at this way. All these points, together with the eye, they will projected into a line. All these points are collinear. They are occluding each other. They are all competing. They all have the same x and y. And will the z-value be the same as the original z-value? Absolutely not. I'm going to completely bully the z-value, change these numbers completely. What am I going to guarantee is that if I have a red triangle, a point on a red triangle, that is a point on a red triangle that is further away than the blue triangle, one point is further away from the other one, then after all this massaging, if it was further away, then it will stay further away. Even though I'm changing the z-coordinate, if something is further away than the other one, it should still be further away. So here are my set of points originally, coming in this order, and here is what they are projected for. And let's see what point is projected to which one. Here I'm at the corner of my original Forstum, set of points just on the boundary, as extreme as it could be, and where they are all projected to, transformed to. It's a set of points who are, what are there. Where do they hit? That would be the lowest pixel in this 1D image plane. In 2D, it would be the corner will hit the corner of the image plane. And that would be for all the points over here. For all the points over here, all projected into which are on the highest image plane. What happened to arbitrary set of points? Projected into over here. Above is above. Above is above. It's like taking the eye way, way into infinity. Right? Now, why is it so crucial to say I give guarantee only for objects which are inside the Forstum? Tell you what is a Forstum, and guarantees come only for points that happened inside this Forstum. Pay attention to this point P. Here is a point P that happily lives inside the Forstum, and P prime is where this point is transformed into. P moves along the upper part of the volume, then P moves on the upper part of this Forstum, and P prime moves along this horizontal line on the upper part of the Forstum. All the guarantees are coming very nicely. What happens when I'm exceeding this Forstum? What happens to P prime? Jumps to some arbitrary point. Remember, I'm still between the near and the image plane, but P prime is going somewhere to infinity, doing various things, coming back if I'll go further away. Projection or between P and P prime loses all guarantees the moment that P is not in the image plane. That is, I do need to define everything so the near and far will be there. One word about why does it all happen. Near plus far minus far. What happens when the z-value is far? What happens when the z-value is, first, what happens to the vector x, y, z? 1, multiplied by this matrix, it will be n times x, nearest times x, nearest times x, near plus far z minus fn, and z, which because of homogeneous coordinates, we divide everything by the last coordinate, and x over z and y over z, blah, blah, n f z divided by z minus fn z, and 1. what happened if Z is near? What happens if Z is near? Where does it going to? The new Z would be n plus far minus far n divided by, we said near, n divide n. So we have as the last coordinate coordinates would be f would be n plus f minus fn. What happens to a point which is already on the near? A point that lies anywhere on the near. Then use that coordinates. Point that is already on the near will, its new Z prime is near plus far minus far, which is near. Map to the near. What happens if P prime is already on the far? Voila, I'm on the far side. The same argument, just replace near by far. You P prime, Z as far, it will be mapped into a point on the far. How do I guarantee these issues that points that are nearby will come in the right order? Well, if I increase the original Z, then this number becomes smaller, but it's with a minus sign, and it's all in the negative part. So yada yada. The order will preserve. So it's becoming smaller, but it's a minus sign. So yeah.
Are N and F, they're just like the Z coordinate of the two?
Yes, but I picked them based on what I want the volume to look like. I can control them to be whatever I want, and it will change, of course. If I want to keep it this way, if I want to keep the I in this part. But it doesn't really matter. I want a different aspect ratio. It will be there. It will be over here. What essentially doesn't matter really where is near and far. It affects the geometry of the shape. What is the aspect value? But all these points change their coordinates completely. But triangles stays triangles. And things that hides things will be projected to things that hide the things. The Z value is all you need to look at. The bottom line is to know if one point is further away than another one, just look at the Z coordinates, as opposed to look at the distance from the origin. Make sense? So now you know what is the whole set of transformations that you need to do in the beginning of your WebGL applications. You have the cameras over here, rotate, translate, decide about the near and far if you want to use them, but you have to use some value of near and far. You don't. And rotate by computing the UVW as in homework 1, translate by change the first rotation matrix, use the code for product of matrices. There is no reason to do it, to calculate matrix products manually. And that's one output matrix that you need to have. Good? And I think that you know everything about this part. And yeah, this. And let's move to start to talk about the part that I didn't speak about that I think that is obvious. You want to scale everything into, so the camera, the canonical volume that you'll end up is, would be, where you're watching it, this would be the Z-axis. You want to map your whole image between between +1 and -1 in the x. Similarly to here, you want to map everything into this canonical volume, which your set of transformation is all in there. What I didn't show you exactly is how to do the translation and how to do the scaling, but it's all implicit. And then to compute from -1 to 1 into 0 and 1, you all know. Translate from -1 to 1 into 0 and 1, you all know. Then move it into I and j, which are the pixel coordinates. You all know. You have coordinates between 0 and 1 for x, same for y. Multiply it by the number of rows and number of columns in your image, and you have the pixel ID. Just as you did in the billboard questions. Should I go back to these topics? You look like I did not really cover it all. I can go through it systematically and do every step specifically, but I think that you have all the blocking, all the pieces that you need. We can decide if you want revision. We can discuss it Thursday, and I can give you more time for the homework. Non-issue. Texture. To start with, I have coordinates of a triangle. I can speak about the homogeneous coordinates, u, v, w, or some linear interpolation inside the triangle. And I have some image. And as an information that is associated with each vertex of this triangle, I can also say, hey, look at this image. Here are the gray level of this image. And these pixels appeared right here on this image. This pixel of this triangle appears right here. And similarly for the third one. And once I told you about these 3 pixels, it's information that I give you as part of the vertex shader. Our GPU will know to find every intermediate points of the pixel by just linear interpolation. And the same way that it interpolates colors, the same way that it interpolates lights, interpolates normals if you are using the Pong shading model. It can interpolate values of I and j and go to the original image, original texture, and pulls up the value that is written right there. And the WebGL will also do all the homography that is involved in it. You decided that this pixel appears right here. Of course, the image will look differently oriented. So what I want to do right now is just to tell you how many other applications of texture you have besides just project a billboard on a shape. So it's more about giving you a feeling where are we going with this. There's tons of mathematical problems if this transformation involves smooth surfaces. It's not only triangles. Suddenly, this mapping is not entirely trivial, and it works all this work, right? Because I can map a texture to our dinosaur to start with, make it looks more interesting. So, but that's so far I just take the color of the skin and project it onto the surface. And to do it, when I'm saying I do it, means I assigned vertices of a triangle to vertices of the texture and tell it how to interpolate. Just linear interpolation or more fancy that we'll talk about. And more fancy might be even if you're talking about I have a map of the world and I have a sphere and I want to map the map of the world to the sphere. The linear interpolation will not work. You need to use different mapping. We'll talk about it. But let's talk about more application of texture. Shadows. Question. How do I asked you in homework 5 and also I asked you in the class, if I want to know what are the which chair do I see right now, how can I do it? With the Z buffer algorithm. How can I do it? just to know which chair do I see. A little trick. Think about the Z buffer as a black box. I take an image, and the GPUs are all arranged optimally to produce the image that I see right now. How do I know if I see chair 17 or not? Chair 17 over there looks exactly like all the other chairs. Similar parameter, similar everything. Chair 17, 18, 19, and so on. And for the chairs that I do see, I'll do something that involves the shading, involves more effects. There are many chairs that I don't see. I don't want to waste any computing time about them.
Shoot out array and determine if...
I can shoot array, I agree, and see what's the first one, but that involves ray shooting. I don't use the power of the GPUs to do it. The GPUs are optimized to death. You cannot beat it by your fast CPU implementation. I have the GPU that is optimized so well to produce images once I'll feed a set of triangles in 3D, and it will produce an image as parallel as your hardware can support. How can I use it to decide if I see chair 17 or not? Involve a little trick. And I'm a bit cheating here that I don't really need an answer if I see chair 17 or not, if I see a significant part of chair 17. If I just see one point, you can say yes or no, up to you. You are allowed to cheat about if it's just a very small portion. If it's large enough portion, I definitely want to know. Yeah? So, yes. I have the z-values of the original chair, and I can go and check for each value that I generated, because I also have the depth buffer. So I can see if the depth buffer fits any of the chairs. But that means a loop that will run for every pixel, check if it matches any of the chairs or not. Agree? If I'll just ask for every pixel, what's the depth of this pixel, it starts well. But if I'm asking which of the chair does it fit exactly, I'm in troubles. I mean, not in troubles, but it's much slower. I need to now run a loop that for every pixel check each one of the billion of triangles that I have, does it match this triangle or not? And I want you to look at the image that you'll produce, and immediately to say, based on this image, yes, chair 17, you do see, chair 18, you don't see. But all the chairs have the same color. The images of all the chairs looks kind of the same. Well, what happens if the chairs don't have the same colors? To be precise, what happens if every chair has a unique color? That is, the color of chair 17 would be RGB equals 0, 0, 17. I'll use it as part of the color. And same for each one of the other pixels. And now generate the image. And if you see chair 17, then one of the pixels in the output image is the color buffer would say, yes, there is a pixel whose color is 17. And you're doing it as a pre-processing stage, kind of similar to how you represent how you generate the mirror in the image. You first fake the colors of all the objects, each one to have a unique color. Do one pass of the z-buffer algorithm, very efficient. And then look at the color buffer and say, oh, based on the color buffer, I know if chair 17 appears or not. And using the depth buffer, I also know how far away chair 17 is. And there is many algorithms that starts by doing this process. of doing one pass when you fake properties of the object. Yes? Make sense? It's one pass of all the chairs when I fake the color of each chair. And then I'll do another pass of the Z-buffer algorithm after I'll compute for the chairs that I do see. I'll perform all the shading and the effects, but only of the chairs that I do see. Generate now a new, change the color of each chair based on the shading, and now make one pass that I really generate the image. What's happening with the shadows here? How can I generate a shadow? I can do the shadow by shoot a ray, find where this ray hits the grass, and now shoot a ray into the sun and see if this ray to the sun is blocked by a tree or not. Doable, sometimes unavoidable if you have a lot of mirrors and multiple of different objects. But now my simple equation is more binary. A pixel seen by the sun or not? Seen by the sun should be illuminated. Not seen by the sun should have a different color. Help?
Do we do like a Z-buffer, but from the point of the sun?
Do a Z-buffer from a point of the sun. See which pixels of the grass the sun sees. Change the color of the pixels of the sun, assuming that it's easier even if you'll assume that the grass is not necessary. If the grass is planar, it's nothing but homography. Possibly I'm thinking about something like this for homework 6, possibly, but it all starts by see what the sun sees. That is, do one pass of the Z-buffer algorithm from where the sun stands, and check which part of the grass are visible and which part are in the shade. And now when you'll generate the original image, you can ask for every pixel, hey, this point is illuminated or not? That's one option. Yes, no answer. Or you can generate the whole grass as a texture, and after generating as a texture, put the whole grass that you see as a little hill over here, putting the texture on one big triangle out there. Both will work. Now, sometimes there are more dramatic effects. You can generate this wall as one texture of the wall. You can generate this wall as one texture of the wall, and the same goes for these two nice gentlemen on the left. But the moment that you start moving, or the player in interactive will start moving over here, you'll see that it's just one big plane. So ray tracing is better, or a solution, because in ray tracing I also know the normal to every point, and once I know the normal, I know what are the shading effects. So ray tracing is one extreme solution, very slow but very accurate. Texture mapping of the original image is another effect, but that doesn't. But you'll notice that as the viewer moves, nothing in the texture itself, in the picture that you see over here, will change. A better solution would be use a texture, but why do you see the dramatic shadows effect, shading effect on their face? Because there is a clear direction of the light, clear direction of the viewer, clear normals that are changing. Let's use a normal map, the same texture, to tell us for every point what we want the normal to be. So it's still 2D faces, but I gave you the extra information of what the normals will be at every point, and use this normal to create the shadows. Again, it's more of a promo right here, but as the surface change, we can control how various attributes, like the normal, change, but still keeps it as a 2D structure. Let's see more examples, and let's keep it as a promo of the discussion. The texture of the shadow over here, the texture of the floor, sorry, as well as but one pass from the sun outside will tell me what is the illuminated part. Change the texture in the illuminated part, but you don't need the ray tracing. It's just 2 or 3 passes of the Z-buffer algorithm over here. No ray tracing necessary for this image, as well as the nice textures that you see on the floor. You don't need to give the whole 2D image of the floor, because as you did in homework 3 or 4, you can do tiling of a much smaller image right there. Skipping a few parts, mapping that is more complicated from surfaces to surfaces, like the global. More applications. Yeah?
With the shadows, I remember when we were talking about making soft shadows, you would have to shoot multiple random rays if you're doing a ray.
Yeah, I can do a few Z-buffer from a few location if I want it to be accurate and do some interpolation between the images. I think that I can also fake it by smear the boundaries of the image a bit, but I didn't decide, and I want to look more if it's anywhere, if the results are anywhere. So yeah, a quick answer is that it works nicely exactly in the effect that I have dramatic impact of a few and light points, sources of light that I want to highlight, that surface and normal and shadow interact with each other, this bump map that are involved. I think that for soft shadows, it's less of, I'm curious about it and I want to look more. Yeah. What happened for this great 3D image? Well, it's not 3D, it's 2D image, except that some pixels are visible, some are not. Similar to what you played with in homework 4. Some pixels are transparent, some are not, and you see through them. But how do you map them? Texture mapping once again. The orange, I play with the normals because there is a point source of light. So the texture now is not the RGB colors, but it tells me, assume that the normal right here is pointing this direction. Use the texture to tell you which direction the normal is. And every pixel will decide if the normal points to the light or away to the light. That would be bump mapping and normal mapping. Various ideas over there. Yeah. Okay. More interesting texture mapping for a non-planar shapes. Okay. Generating kind of similar to soft shadow, the soft effect of the lightning and the specular effect on the floor, which again, a few passes. Environmental map that you can definitely implement in homework 5. Either generate the image surround you, but now it's on a sphere. It requires some pre-processing, but what will be the result of this projected onto the sphere? You can take the Tucson cap. You can take the image of the world around you, and the world around you can be represented as 6 images of the back, forth, the worlds around you, or it can be projected on a sphere and you're inside the sphere. And now you can use it as a texture, map it into low resolution, but map it to as a reflection on the cap, on the Stanford cap. Let's see, more example, environmental map. Here are the cube maps. That are 6 images that you can represent in homework 6. And as I said, you are inside the room, and when you generate the texture around you, you don't see where these boundaries between the different images will vanish when you look at if my camera points directly into where the ceiling and the wall meet, I don't see where they are connected. There is no discontinuity over here. Leaf map, which is interpolation, some mixture between ray tracing, but very limited ray tracing, where the texture just tells me, oh, you're only ray tracing debate, are your ray hits on the top of the brick or between the bricks. I'm not doing global, very, very slow ray tracing between all the objects. I already know that all my rays in this part will hit the floor. I'm just debating a ray hits this part or this part, and that will require 3D, but very, very limited transformations. The relief map will be extremely useful for generating very large, very, very large inputs. Okay, old NVIDIA. Very much related to how do I generate very large environment, as well as why do I store when I have a very large model. Do I store it in high resolution or do I store it in low resolution? I have a Stanford bunny. Do I render it with all its 73,000 triangles also? Do I store it with only 100 triangles also in much level resolution? What do I keep in memory? Answer, keep both or keep a few levels, and based on how far away the Stanford bunny is from the viewer right now, and at which resolution you are presenting it, pick the object that you put right there from this part of a few level of hierarchy of details of the same Stanford bunny. Does it take a lot of memory, the fact that I store the same thing several times? Not really, because if I store this one, then this plus this plus this adds only 1 plus half of this plus quarter of this plus 1/8 of this. It all sums up to at most 2 times factors, and it's much, much quicker rendering when the bunny is, of course, far away. And you're doing the same thing for texture as well. Keep the image of the texture either in very high resolution or in very low resolution, depending on how far away and what level of details you want for this object right now in the game. Okay, many more applications of texture mapping. One specific image that I want to show you, if I'll find it. Yeah, never mind. Later. Thanks. Okay. And sure. And sure, let's spend on Thursday 15 minutes putting all the transformation together, arrange them as a one single pipeline. Somebody forgot a cell phone.